Welcome back to CDR. I hope you had a good weekend. I hope you had a good exercise on Thursday. And this is actually what I would like to do first today, to talk a little bit about what we saw in this problem 8, where our basic idea was that you have a coordinate system in some orientation at time t0, given, of course, through a transformation matrix. So someone gives you an AIC at a time t0, which defines an orientation of a coordinate system. And then the same person gives you a angular velocity vector of that same coordinate system. In this case, the angular velocity vector was given in I coordinates, and it was constant. I think it was just 1, 1, 1, basically a rotation about sort of this space diagonal. That was your rotation axis. And your task was to compute AIC as a function of t. So how does the transformation matrix change over time? Or in other words, how does the coordinate system change over time? And we did this two ways. Number one was this guy here. We simply took our equation for that related AIC and its derivative with omega IC and solved that for AIC dot. And that gave us this expression, and then we integrated it.
The library for these doesn't work on the R4, only on the R3, so I can't make it work sadly.
And we don't have an R1 downstairs.
I have a mega. I have to try that. It'll probably work. Will I catch it?
Give it a try. Yeah? Because I have, but this is also, you want to try this? But that's the same guy. That's the same guy. Yeah. Oh. So, sorry. Sorry about that. This is how you should never do an integration. Compute the derivative, and then you do an update. AIC is AIC plus AIC dot times delta t. Right? That's a stupid Euler forward integration. We did this here to prove a point. And then that's our integration. And then all we did is we updated our coordinate system. So this is the set command, set.aic, c.aic is set to this transformation matrix. And then I do a draw now to update the screen. So let's see what happens if I run this. And I should say I haven't tried this before class because I was busy with this guy. So this may be another thing that doesn't work. Okay. Sorry, in trying to fix this, I broke that, and so I don't have internet, and I need internet to access MATLAB. Because these files are on the network drive, and I cannot access the network drive. Sorry, I'm just contemplating whether it's worth restarting my computer.
Is it possible to connect to the free Wi-Fi?
No, my Wi-Fi adapters experience a malfunction, so I would have to restart everything. Let's do this, because there's a few things that I wanted to show you today. This is why we normally don't do live demos. It's bound to screw up things. Depending on how far you are, we could do the other demo.
1 second. Yeah, should work now. It's on the Arduino.
Okay, can you connect it so I don't break it again? All right, this is.
Okay, you just have to turn it on and then it should be fast. Maybe press the reset button on the Arduino.
Is it possible that I screwed the?
Power supply.
No. Okay, it does not work, but it seems like the Arduino is not getting any juice.
Doesn't.
It does not.
Maybe you can just connect it to the power supply.
Because that went so well last time. Okay, no internet. Nope.
Is the light on the Arduino on?
No.
No. Okay, that's weird.
Nope, no light.
No light, but that's because it was working just like 2 days ago.
Yeah, it was working before someone touched the wires and screwed everything up. Okay, we're gonna table this demo until Thursday, maybe Thursday next year. We'll figure it out. We go back to this, and I just want to show you the run. Now, hopefully this works, that I have internet. Yes. So what you saw on the screen is solution to problem 8a, where we had this coordinate system, which basically started in this rotation and this orientation, and then we rotated it about this axis here, this vector here, that's my vector omega, and then we let this rotate such that we should get one full rotation. And doesn't look too bad, not too shabby, right? Here's our rotation. What's the problem? Why should you not do this if you're trying to track the rotation of a coordinate system? And I can increase the effect by going to a smaller number of steps, right? Smaller n means larger delta t, because we do this for one rotation, so we got a quicker rotation, fewer steps to animate. There seems to be a problem. What's the problem? That is also a problem, but what's the bigger problem?
The rotation wasn't smooth enough, calculated, kind of.
What's the real issue here? Come on, guys, look at that screen. Look at that red coordinate system. It didn't do a full 360 rotation, but look at this coordinate system. What's the problem with the coordinate system? It grew. My coordinate system is not a coordinate system anymore because it should consist of unit vectors that are orthogonal to each other. And whatever these red things are, they're not unit vectors, right? Green is a unit vector. The coordinate system grew, right? And if I would go ahead and carefully measure angles, I would see that they're not orthogonal to each other anymore. So my coordinate system stopped being a coordinate system in the sense that the transformation matrix AIC is not orthonormal anymore. This is where I screwed things up. Why does that happen? Wrong lecture. Here we go. Why does this happen? Well, we do the stupid integrator, which basically says, does an Euler forward step, where it assumes that over this duration delta t, AIC dot is constant, which is not true, because over here we see that AIC dot depends on AIC, and if I have a rotation, AIC changes, so AIC dot changes, and here in my Euler forward integrator, I make a mistake. Right? I assume that this is constant, that's a numerical approximation, amplified by the fact that I'm doing just a few steps, and I then end up with a numerical error. And that numerical error is in AIC dot. And I integrate it, and it means my AIC gets screwed up. Right? I don't get the correct rotation, but actually that's the least of my problems, because AIC is not a transformation matrix anymore. Right? That's a huge problem. So never ever do this. Because if your transformation matrices are not transformation matrices anymore, you're thinking you're rotating something, and in reality, you're scaling it up. So very, very bad idea, right? We want AIC to be an orthonormal matrix, and that's not happening here. Comes in 8b, second idea, where I said, well, can I actually write this transformation matrix as a function of three angles? And here we use the Cardan convention, so alpha, beta, gamma are rotations about three coordinate axes. I think it's axis 1, axis 2, and axis 1 again. Was that correct? Doesn't matter. But something along those lines, three rotations. And we then had a look at this and analytically computed this matrix, right? So I know AIC as an analytic expression of alpha, beta, and gamma. I analytically computed AIC dot, multiplied those together, got this guy here, omega tilde, extracted omega IC. And we saw that this, of course, then depends on alpha, beta, gamma, as well as of its derivatives. And it turned out that the derivatives were sort of nicely stacked here in the back and everything, or we were able to stack them nicely in the back of some matrix B. In other words, this vector omega ICC is linear in the velocities of the Cardan angles. I think in the exercise you discovered this more or less by chance. Right? You computed this expression and then thought about a way of extracting it this way. But it shouldn't surprise us. Why should that not surprise us? Well, if you think about this matrix AIC being a function of alpha, beta, and gamma, and I want to compute AIC dot. One way to do this is to apply the chain rule and say AIC dot is equal to partial A partial alpha times alpha dot. Right? That's the chain rule. Instead of taking the time derivative of the whole thing, I take the derivative of A against alpha multiplied with alpha against time, alpha dot, right? And then I do this partial alpha, partial beta, beta dot, and so on. So that's always possible. We'll see this later when we talk about Jacobians, that velocities are always linear, and that linearity comes through this partial derivative. This is also how you did time derivatives in MATLAB, right? I asked you explicitly to not use the diff function, but instead use the Jacobian function and go through this process. So this here is always possible. And now I have a relationship that I can invert, and I can compute alpha dot, beta dot, gamma dot as a function of AIC of this matrix B. Right? So I have to bring everything on the same side. So there's an inverse here, and of this vector omega ICI. And that gives way to a second way of integrating rotations, where we do the integration on the Cardan angles. So at every step, I compute this matrix here. Based on that matrix, I compute these derivatives. I integrate them, right? This is again the stupid Euler forward integration. So alpha nu is alpha old plus alpha dot times delta t, right? And the same for beta gamma. And then I use this function to assemble alpha, beta, and gamma back into a rotation matrix and apply that, update my graphics window. And this would be solution 8b. Where's my loop? Let's be fair. Let's also do 50 steps here. And let's see what we get. Yep, that was too quick. Let's try again. There's our rotation. What did we fix compared to case A? They're unit vectors, and they're orthogonal. And that shouldn't surprise us, because this AIC is computed in each iteration anew, right? I get new Cardan angles alpha, beta, gamma, and I use them to compute a new coordinate transformation. And of course, that process, right, I put together 3 elementary rotations. I get a nice transformation matrix. Do I get what I want? Not quite, right? We were hoping to get a full rotation. Here I have a bit of an error, and I can make that error a little bit larger if I take fewer steps, quicker motion, and we see, right? We don't get there. Same problem, right? Numerical integration. I kind of assume that the Cardan velocities are constant over a period delta t, which they're not, because the Cardan angles depend on AIC, which depend on the Cardan angles. So there's sort of this chicken and egg problem that you see in these differential equations, and that now leads to an error. But the error is sitting in the Cardan angles. So a full rotation is not a full rotation, but at least my transformation matrices are the same. There's still a problem with this, and that problem has to do with the -1 that we see here. Right? We're inverting this matrix, and whenever you invert a matrix, you ask yourself, can I do that? Right? So compute a determinant, figure out is the matrix singular. In this case, we can actually do an analytical inversion, and if I do this in MATLAB, I get this expression for AIC times B inverse. Right? That's my matrix here. Who can see a potential problem there? If this guy is 0, cosine beta, then all of these, right, the tangent and the 1 over cosine become infinite. So we have an issue here, right? So for beta equals 90 degrees, we have a problem, right? This matrix here becomes singular. That problem is called gimbal lock. What is happening here physically, right? Numerically, I know if this becomes 0, then I cannot really invert this matrix, and these values would become infinite because I have a 1 over 0 in here. So numerically an issue. What is happening? What is happening for beta equals 0? And here is a solution to problem 6, where we have these 3 rotations. So we start with the green system, inertial, red system rotated about the 3-axis, blue system rotated about the rotated 2-axis, and then the purple magenta system again rotated here. So we have green, red, blue, and purple. And those are my 3 Cardan angles. And then I said the issue is if I set beta to 90 degrees here. So let's set this quickly to 90 degrees. And let's see what happens. So my first rotation between green and red is about the, what was it? 3-axis. Oh, sorry, I should read this backwards. About the 1-axis. Then I get the magenta coordinate system here. Then I rotate about the 2-axis to get the blue coordinate system. And this rotation is 90 degrees, which basically means that the 1-axis of the blue system now lines up with the 3-axis of my original green system or the red system. And now I rotate again about this axis. So in 3D space, I did a rotation about this axis. I did a rotation about this axis, which happened to be 90 degrees. And then I rotate about this axis. That axis and that axis are the same. So through this beta equals 90 degree rotation, I aligned this axis with this axis. And my 3 rotations essentially become 2 rotations, right? Because the first and the third rotation is about the same axis. So they do the same thing. And this then leads to the fact that I cannot invert this matrix, because if I'm now going backwards and saying, hey, I give you some arbitrary angular velocity, can you give me the 3 Cardan angles that result in this velocity? The answer is I cannot, because alpha dot and gamma dot are giving you exactly the same rotation. So I could have either alpha dot 1 rad per second and beta dot 0, or the other way around, and would do exactly the same thing. And because of that, I somewhere else lose an axis, right? In this situation, I can only rotate about this axis and sort of that axis, and I cannot rotate about any axis that's perpendicular to these 2. So that's where I lose a degree of freedom. This is what's called gimbal lock, which numerically manifests itself here. Now, you could say, okay, that's simply because your professor is stupid, you know, he can't even get hardware to run, can't handle his computer. For sure, he doesn't know a good way of picking these 3 angles, right? Maybe you just use a different convention. You go 1, 3, 2, right? Or 1, 2, 1, or 1, 3, 1, right? Maybe it was just me with this convention, 1 axis, 2 axis, 3 axis, that screwed everything up. Turns out, you always run into this problem, because your rotation about the 2nd axis can always align the 3rd rotation axis with the 1st rotation axis, no matter what you do, right? Or the combination of the first 2 can do that. So you can never get around this problem. How can we get out of this? And there's many ways to do this. Number one would be to pick a representation where this doesn't occur in daily life. So if you think about an airplane, for example, it normally has that orientation, right? It banks a little bit, goes up, goes down, rotates about this axis, full 360, but the other two axes are fairly limited. So pick a representation where gimbal lock doesn't show up when you do this, right? When you think about a legged robot, same story. Your main body should mostly be upright, right? If your head is pointing down, you have other problems than gimbal lock. So that works, right? You can try changing your representation. So you have a 1, 2, 3 axis, and when you're getting close to gimbal lock, you flip and say, okay, let's go to a different representation, 2, 3, 1. Right, and stay in that until we get closer to that gimbal lock, and so you go back and forth between representations. But the general problem is basically that 3 numbers is not enough. Right, you always get the singularities if you have a representation by 3 numbers. Here we don't get singularities because we basically represent the orientation by 9 numbers. Right? And that over-representation introduces or gets rid of the singularity, but introduces this other problem that we would have to make sure that basically the constraints that come with this matrix are fulfilled. So I could try to do this, and after every step I do a normalization of my rotation matrix. Right? So I renormalize all vectors, I make sure that they're orthogonal, and I basically do a renormalization of this rotation matrix. And then I could use this approach, right? I would just constantly have to make sure that this is actually a rotation matrix. And then what people would do for real, and this is, we will not discuss this in this class, is using quaternions, which is basically a middle ground between these two approaches. You use 4 numbers to describe a 3-dimensional rotation. And then when you integrate, you will run into a similar problem as you do here, right? Because 4 numbers only represent their orientation if the norm of this quaternion is 1. And then if you integrate, the norm will change. So you have to basically constantly renormalize your quaternion, your representation with 4 numbers. But that normalization is much easier than what we see here. Right? So that could help here as well. What will we do? And there was this question at the very end, right? How can we change a single line here such that we get a perfectly accurate rotation? Right, so there's a little trick that we can do. Did anyone get the solution? Anyone has an idea? You got some?
We can use that in the problem velocity is constant. So we can
that helps, but then how do you solve it?
So my idea was essentially, since it's an ODE, MATLAB can calculate the exact solution. In German it's Transitionsmatrix, E hoch AT.
Okay, let's look at this. Here was our base idea, right? For problem A, we said we have this derivative A dot is omega ICI times AIC. And that's a differential equation. It's actually a linear differential equation on a matrix, right? It looks a little bit like something that you may have seen before, where you say x dot of t equals, and then this is now confusing you, but this is how you normally write this. X of t is a times x of t. Right? This is a standard linear differential equation. X dot equals a times x. And you all know the solution to this. So x equals e to the power of at. So here we have a matrix exponential times x at time t0. Right? And these, to be fair, should be all vectors. Right? This is what you know from controls. Right? The analytic solution to this differential equation is this expression here, where I have this matrix exponential, which depends on time t, and I multiply this basically with my initial conditions. And the analogy here, of course, is that x corresponds to our matrix AIC, and then the matrix A of our linear system corresponds to this omega IC I. So those two are analog, and that means that I can now go ahead and apply the same approach and say that my AIC at some time t plus delta t is going to be the matrix exponential of omega ICI multiplied with delta t, and then that whole thing gets post-multiplied with my initial condition, which in this integration step is basically AIC at time t. And that line simply replaces this line, right? Here my stupid integration was AIC new is AIC old plus AIC dot times delta t. Here, AIC new is sorry, that is the old. I was looking for this guy. He's hiding it for suspense and then didn't find it. Here we go. AIC new is matrix exponential times AIC old. That is now my update step. And then this line here, up here, that is not even needed anymore, right? I don't need AIC dot in this expression because everything is directly based on omega tilde. But the challenge was to just change one line. That's why I left it in. So that's the only line here you have to change. So you're analytically solving the differential equation over one time step. With the solution here, it comes with this matrix exponential. And for omega IC being constant, which it is in our case, this is now analytically exact. So if I go to my example 8c, where this is implemented somewhere down in the weeds, and I now run the animation, I get a perfect rotation, right, using the matrix exponential. And if I go down to 20 steps, still a perfect rotation. If I go to 2 steps, bang, bang, perfect rotation. So that matrix exponential helps me to keep my matrix orthonormal. Is that also more efficient? Right? Before, right, when I was doing my other approaches, I had to do 100 steps to get a roughly correct answer. Here, I just, I could in theory just do one time step. And for omega being constant. Of course, if omega changes over time, then different story. But for omega constant, I still get an accurate solution. So which of these approaches is more efficient?
I guess it would depend on the situation you want to use it for.
Efficient from a computational perspective, right? And what I'm trying to get with this is I could do, in problem, let's say 8b, I could do this 1,000 times, right? And I would get a fairly accurate representation. And I could do this 1 time, and I would get an accurate representation. There's, of course, right, everything is done numerically, so there's going to be some small errors. Which one is more efficient? One would think, right?
Depends on the computation involved.
Depends on how much it takes to compute this, right? And this is something where I just want to warn you, right? We like to write down, oh, right, you just have to compute this matrix exponential, and you're done. Yeah, analytic solution, boom, yeah. How do you compute a matrix exponential, right? It's defined as an infinite sum over, matrices multiplied with each other. And so in the background, there may easily be 1,000 steps involved to compute this matrix exponential. Right? And I don't really know how MATLAB does it. There are certain algorithms that are more efficient. They're basically based on taking the square root of your matrix until it's small enough, and some polynomial approximations works, and then you scale it back up again. And maybe there's tables in the background that help make this more efficient. But in the background, you still have to compute this. So I would not claim that this is more efficient. Right? It's well possible that this allows you to work with fewer steps, but that each step is much more expensive than doing what is shown here, which are simple additions and multiplications. Questions? This is what we're going to use throughout the rest of the class. So exercise 3, as a preview, we're trying to now simulate the rotation of a body, which means we somehow compute the angular accelerations and then integrate them. And that integration is going to be using this step here in the background. Then I want to go back to our Newton-Euler equations for rigid bodies, where what we saw was on the physics side of things, we have something that's fairly simple. Sum of all forces is the change of linear momentum. Sum of all external torques is the change of angular momentum, where that equation only holds if my reference point is the center of gravity or something stationary. If I allow for moving reference point, then I basically have to compensate for the non-physical effect that a motion of my reference point seems to change the angular momentum, even though physics is not doing anything. And we then looked at an example where we had two particles like this, one here, rotating in this moment about, sorry, this is better. This is rotating about the z-axis, or sorry, the 2-axis, and we went so far that we computed the angular momentum, which points this way. Mass here, rotating this way, so that's my omega. Angular momentum points this way. And we did this through sort of the definition of the angular momentum, compute the linear momentum, and then the moment that it creates, so literally the moment of momentum. And then we did it through the mass matrix. That's the same thing. Now, the question, of course, is how does this thing move? Right? What happens next? And the assumption here is that I have no external force, no external torque, so they're all 0. And the first assumption would be, well, if in this situation I'm rotating about this axis, I have no external torques, I should see no angular acceleration. So a common assumption would be to say my omega b, my angular velocity, is constant. If I now wait for some time t equals pi over omega, which is me just saying I wait for half a turn. Right? So I'm rotating about this axis with half a turn. My original image has flipped, and sorry, I'm just doing a crude sketch here, but I would continue rotating about this axis, omega b. I have my two masses. Now, since I'm rotating this way, this mass is moving into the screen. That mass is coming towards me. So this would be velocity 2, velocity 1. So I started like this, rotated. Sorry, why is this so hard? I started like this, rotated. This mass is moving this way, that mass is moving that way. This mass impulse in this direction, so I get impulse cross lever arm, angular momentum that way. The same down here, so my angular momentum points this way. This is LG. That cannot be true. Right? It was pointing this way. Now it's pointing that way. So the angular momentum has changed. But we had no torque. And if there's no torque, right, torque is equal change of angular momentum. If there's no torque, angular momentum cannot change. This is not true. Right? So if I assume angular velocity is constant, I would see that my angular momentum changes. But the equation says if torque equals 0, derivative of angular momentum is 0, angular momentum must be constant, not conserved. So what we see here is that omega b must change. Even if the torque is 0. Somehow we see an acceleration even though there's no torque. Completely different to what we know from translational motion, right? If there's no force, there is no translational acceleration. But here, apparently, there is a angular acceleration even though there is no torque. How large is that acceleration and how do we get to it? And this is where I start by basically restating where we started, that the change of angular momentum is equal to all torques. Written here as something physical, and now I want to express this in a body-fixed coordinate system. So I can simply write little b's here. I'm waiting for someone to complain. This is wrong. What I just did is wrong. Something is missing. Correct? Still correct? Wrong. The brackets are missing. Thank you. Right? When I express a physical derivative in a coordinate system, I have to make sure that I really say I want this physical derivative in b coordinates. What I wrote down was the change of numbers of L dot, right? And those two are connected through the transport theorem. So if I resolve this, I get the numerical derivative plus this expression that comes from the transport theorem. And since omega IB in this case, our small omega IB is simply the omega B, the rotation of my body-fixed coordinate system, I write it this way. And I get here omega b tilde times LG. So this is the transport theorem. Then I can go ahead and say, now I'm doing numerical derivatives of my angular momentum, right? And the angular momentum was defined as angular velocity multiplied with our inertia matrix. And that's a numerical expression, right? These are matrices or matrix vector multiplication. I want to take the derivative of this. So I have to apply the product rule, and I get IBB dot, a numerical derivative, not a physical derivative, times omega b times the coordinate vector of omega b plus IB b times omega b dot. And now comes the reason why we do everything in body-fixed coordinates. right? Body fixed coordinates are annoying because you have to remember to use the transport theorem. If I had written I here, this would be okay, but I wrote B, so I have to compensate for the motion of the coordinate system. But what's the big advantage now? Say that again? This one is 0. Right? We have to figure that out once, and in body fixed coordinates, the inertia matrix has a constant representation, so its numerical derivative is 0. And we thus get that the sum of all moments about B is the inertia matrix, pardon me, times the angular acceleration plus omega b tilde times, and Lg I can write as the inertia of this body. Sorry, there should be a G in my inertia matrix because it's the inertia relative, or the inertia about the center of gravity. And then here omega comes in as a vector. So this is now the expression in coordinates, right? Physically, sum of all torques is change of angular momentum. Here in coordinates, I have sum of all torques is change of angular momentum. And the change of angular momentum comes from two things. Number one, right, my angular velocity changes. So I have an angular acceleration, and that, of course, changes angular momentum. Number two, back here, my mass rotates and the mass distribution changes. And that, of course, also generates a change in angular momentum. So if I go back a couple of pages, I still have to fill in the equations in coordinates. So this is on, what is this, page 4, where in translational motion, things are simple, right? I say this is the change of linear momentum of your impulse expressed in b coordinates, and that I can write as mass times the change in velocity, specifically the change in velocity of the center of mass. Right? And here we have an assumption, right? We say mass is constant. And the physical change in velocity, of course, is what we would call the acceleration. So that is expressed in b coordinates as well. So sum of all forces is acceleration times mass. For rotations, when I write this down, I have to be now careful to carry the parenthesis, which gives me the numerical change of the angular momentum plus the effect that comes from the changing coordinate system. And I can now express that in terms of angular accelerations and angular velocities by using the inertia matrix. And what we got was inertia matrix times angular acceleration plus what came from the transport theorem which is basically the cross product of angular acceleration and angular velocity. The cross product of angular velocity and angular momentum. And the angular momentum I write as I times omega b. So some similarity, right? Here I have mass times acceleration. Here I have mass times acceleration. But then for rotations, I have this term back here. Where does that come from, right? Why does that not show up here, but shows up for rotations? What is different? And it has to do with actually this assumption that we made here. Right? In a translation, if an object moves, its mass doesn't change. If I have an object and I rotate it, its inertial properties change. Right? In this configuration, the mass is oriented along this axis. If I rotate a bit, the mass is now oriented in this direction. So our inertia matrix in body fixed coordinates is constant. But if I look at it from inertial coordinates, right, if at every point in time I would compute my inertia matrix in inertial, in world coordinates, I would see that the inertia changes. And that, of course, is similar to an m dot. And this is basically what we have back here, right? So I have inertia times change of velocity plus change of inertia times velocity. So in a sense, all we see here is a product rule where this term here, omega tilde times I, gives me the change of inertia. And that's why we see here an extra term. Still asking ourselves, how does it move? But now we know there has to be an acceleration. And I can now go ahead and compute this acceleration by simply saying omega bb dot is given as the inverse of the inertia matrix times, and then I have mgb minus omega bb tilde igb and omega b in b coordinates. That's my angular acceleration. And we immediately see that even if this is 0, right, even if I don't apply a torque, then this guy here in the back still contributes and generates an acceleration. So this creates an acceleration, omega dot. The term back here is called the precision moment. Right? If you compute it, you see it, right? I have a torque here, and whatever I subtract from this also has to have units of torque. So this guy here is a virtual torque. This is called the precision moment. So in our case, right, torque is 0. This will contribute. We get an acceleration. Now, the question is still, how does it move? Right? What motion do we get? And this is now a little bit anticlimactic, because the answer is, I can tell you. Why can't I tell you in this particular case how it will move? It has to do with this inverse here. Today we talk about matrix inverses and what problems they cause. In this particular case, this cannot be inverted because this body consists of a point mass here and a point mass here. Right? They sit on a line, and basically physically any rotation about this axis would not involve any mass. So if I write down the inertia matrix for the system, I would get on the diagonal something like M1. Didn't we write down the inertia matrix of the system? But in xy coordinates. Sorry, if I compute the eigenvalues, I should say it this way. If I compute the eigenvalues of this guy, I would get something that has inertia. Inertia has no inertia. And of course, the coordinate system in which this would show is aligned sort of in this direction with this connection here. Any motion around this axis doesn't see an inertia. And hence, we will not get an answer here because this thing is not invertible. I wanted to show you, nevertheless, a version of this. And to do this, I manipulated the values a little bit. So here we had, if I set x and y to 1, I would get 1, 1, minus 1, minus 1, 2. And what I did here is I added a tiny bit here and subtracted a little bit here to add some inertia around the long axis of this object. So if I show this, here's my output. I would get something that basically has a representation of something that's very, very long and skinny, but has still a little bit of mass, in a sense, around this axis, right? So a little bit of volume around this axis. This is my setup, right? My initial angular velocity is about the 2-axis. My initial angular momentum vector points to here. Here would be point mass 1, point mass 2, and then I added a little bit. And then in black is the coordinate system that is attached to this body. And then I can go ahead and let this move. And on first glance, this looks incredibly complicated, right? Especially if you look at this black coordinate system, which does this complex rotation. And we see the vector here in yellow, that's my angular velocity that's moving all over the place. And the reason why it's moving all over the place is because I have a purple vector, which is an angular acceleration. Right? At every point of time, I get an omega dot, and that changes omega, and then that changes the orientation. What we also see is that this vector of angular momentum, LB, is absolutely steady. Right? If there's no torque, angular momentum does not change, and that is not a bug, right? That's recomputed in every integration step. It's not moving. If I look along the angular momentum, things look a little bit better because I see that the angular velocity vector is basically rotating about the angular momentum vector. And it's doing that because the angular acceleration vector is always perpendicular to angular momentum, which points right at us, and angular velocity, which is the green arrow. And the reason why that happens is because what we see back here is basically a cross product, right? I have the cross product between angular momentum and angular velocity. So I say angular velocity points this way, angular momentum points that way, and then the angular acceleration, or the result of that term in the back, is basically pointing this way. So simple cross product. There's a minus sign, and there's a few more things happening, because if you look here, right, this gets a minus sign, and then it gets multiplied with this inverse matrix. So I'm not directly looking at an angular acceleration when I say I do my cross product between velocity and angular momentum. Right, if I do that, I basically get this times that gives me a vector in this direction here. Then there's the minus sign, gives me a vector in this direction, and that gets scaled with 1 over mass. But that kind of explains why angular acceleration is always perpendicular to angular momentum, which means that, angular acceleration is perpendicular to angular momentum and angular velocity. Since angular momentum is constant, it means I'm driving my angular velocity vector in a cone around the angular momentum vector. And I show you the whole thing one more time. Where you can see that this vector is basically creating a cone around the angular momentum vector. My computer is dying. And then if I look straight along the angular momentum vector, I can see that the motion is actually quite simple. Don't touch it. These vectors, angular velocity, angular acceleration, are always orthogonal to each other. And in terms of this object, if you just look at the blue object, it's just spinning, and it seems like it has a constant angular velocity, but what we don't see that it's also spinning around its long axis. And this is what we see when we look at the black coordinate system. Right, so that the whole object is spinning about the angular momentum vector and then spinning around its long axis. Good. Do you have any questions at this point? I consider all of this still to be a recap, right? You should have seen this in some dynamics lecture before. My goal, repeat and add a little bit of intuition, show you things. What we just did is going to be exercise 3, right? So we will create a function that's called compute natural dynamics, which basically computes the acceleration based on the assumption that this is 0. And then we will implement sort of this integration step that we just looked at, so that these angular velocities, angular accelerations are integrated into angular velocities and then into orientations. And after this exercise 3, you will be basically able to generate that animation yourself, right? So this is, in a sense, that's the solution to exercise 3. There's a few more things that can be said about the inertia matrix IG. I did those in class in the past. I realized that they're not as important for what we want to do, and that a lot of people already know this, right? Properties, symmetry, when are the off-diagonal terms 0, what are principal axis, inequality of the diagonal terms, and so on, the parallel axis theorem. All of this is more or less just a repetition of what you've seen in, what you ideally have seen in your dynamics classes. If you have not, I have past recordings of this, and we will put it on Ilias, so you can watch basically that part of the class at home, but my experience in the past was that this is not necessary. Where I want to continue is to make a bit of a small jump, where so far we only talked about systems of particles. Right? We never really discussed rigid bodies. All the examples that I gave you were systems of particles. And we had in the computation, for example, of our inertia matrix, we had these sums. Here's a sum in the equation for angular momentum. There's a sum. So everything was defined as sums over individual particles. I think the transition from systems of particles to a continuous body right, that transition is quite simple. You simply assume that your body is made up of particles, and you let in your head that number of particles go towards infinitely many. And what that means, that everything that we wrote as a sum over n particles, where something was then multiplied with the mass of the particle mi, turns into an integral, which is nothing else than a sum over infinitely many particles, right? And we just say we integrate over the body. So integrate over all the particles that are part of the body. And because they're infinitely many, each of them has an infinitely small mass. So we will talk about an infinite mass, or infinitesimal mass, sorry, dm. Other than that, right, this and this is basically, that's the limiting case of this for infinitely many, infinitely small particle. So we said, for example, the total mass is the sum over all the individual masses of the particle. So I say m is the integral dm. So I integrate over the mass. Impulse, sum over all particles, where each particle was or the velocity of each particle was multiplied with its mass. Now I write this as integral over v dm. And the same for all of these other quantities. And we kind of see the structure, right? Everything that we defined had this mi in there, and that mi now becomes our integration variable dm. So integrate over the body dm. And the things that we need to compute, right? Our inertia matrix, our center of mass location, angular momentum, linear momentum, kinetic moment, they all have this m in here, so we can easily convert them into such an integral. Questions? I don't want to spend more time on this, but we can do an example. And the example is here a cylinder, something like this. And I want to compute its one entry of its inertia matrix, actually the 3-axis, so the bottom right element of the inertia matrix, which corresponds to the momentum, the moment of momentum, sorry, the inertia, inertia about this axis. The definition was so far, right? You integrate over all particles over these values rho 1 and rho 2, position in the 1-axis, 2-axis. Here we now have the integral, and I basically have to compute this integral over the body x-coordinate square, y-coordinate square, dm. And the issue here is that body is defined geometrically, right? I said it's a cylinder, and this is a mass property. So I somehow have to bring mass properties and geometry together, which normally only works under certain assumptions. And the most important assumption here is that the body is homogeneous with homogeneous density. So I can make a direct relationship between volume and mass. And with that, I could go ahead and basically think of a little element that looks like a square, but remember there's a cylinder. So what I actually have drawn here is the cross-section of a rectangular slice through the entire cylinder. And if that has some size dx, width dx, height dy, what would be its mass, right? And I'm using here dx dy because in the end I let those two quantities go against 0. How large is dm? Well, if I think about a cylinder, the total mass of the cylinder, m, and then I have a total cross-section, which is r squared times pi. Right? So if I think about this, the entire cylinder has mass m, total cross-section r squared pi. This little slice here then has a corresponding fraction of that total mass. So I take the total mass and multiply it with the area of my slice, or the cross-section of my slice, dx dy, divided by the total cross-section. That's the fraction of cross-section that I get, and if I multiply this with m, I get the fraction of mass. And that only works for homogeneous bodies. The reason why I do this is because I can now go ahead and write this integral over our body, dm, as an integral over geometry. As a double integral in x and y. I can change the term in here, right? That's still x squared plus y squared. But now I use this expression here to replace my dm. So my small m is m over r squared pi times dy dx. And we kind of see that I translated this integral over mass and the body into an integral over x and y, double integral over my geometry. From what are the integration bounds? From where to where do I have to integrate x? Negative r to positive r. From where to where do I have to integrate y? I'm glad that you say that. Please don't copy. If it were negative r to positive r, what geometry would I describe? I go in the x direction from negative r to positive r, and then the y direction from negative r to positive r. A square, right? Sorry, this is not a square what I drew here. Actually, from here, for you, it looks like a square. For you, it's probably not a square anymore. So that doesn't work. What do I have to do instead? Right, this is basically the situation where my integration range in the y direction depends on my location in the x direction, where I can create sort of here this rectangle and then go through the Pythagoras, right? Where this distance here is r squared minus x squared, and then the square root of that. So my integration bounds in the y direction are minus r squared minus x squared all the way to plus r squared minus x squared. I need that space in just a second. And this is now something that I could solve. Or at least I could try, because solving this integral is a nightmare. Still okay to get, integrate this against y, so you get x squared y plus 1/3 y to the third power, and then you insert these, and then all of a sudden you get expressions that are like the third power of the square root of x squared plus minus r squared or something like this, and then you need an integrand of that, and you're screwed. How else could we approach this? Change the coordinate system? To what?
X will be equal to the variable r times cosine of the angle. Y equal r.
Okay, but this is rotational symmetric, so if I rotate my coordinate system, I end up with the same problem. I thought you meant something else.
Change the coordinate of the integral. Or change the square system again.
But to what, right? To what coordinate system?
Theta.
Polar. So the idea would be to go to polar coordinates, because here the geometry is given in terms of a circle, right? And describing a circle through little rectangles is not a good idea. So the basic idea is that I create different little mass elements dm, and the idea is to make essentially little rings here, or tubes. So in a sense, right, I'm slicing now through the entire cylinder, and I cut out a tube, and the tube has a radius of r, and it has a thickness of dr. The area of this tube, so dA, the area of this tube, is basically the small dr, the width of the tube, times its circumference, the circumference being 2 pi r. That is the area of this blue thing here. And now I can write my dm, the mass, maybe I write this in blue, just to stay, it's now a different dm, but dm is now going to be mass times 2 pi r times dr divided by r squared pi. So under this assumption it's a homogeneous body, I can go ahead and compute the mass of such a tube. And if I now try to evaluate the integral, over the body, x squared plus y squared dm, we see how this pays off, because the first thing is, in this blue area, and this is the only reason why this works, in this blue area, the expression x squared plus y squared is constant. What is x squared plus y squared in my little tube? R squared. So I replace x squared plus y squared with r squared. And if you ever do these little mass elements, of course, whatever function you have here has to be constant within a mass element, or at least constant in the limit, right? If I let dr go towards 0, everything x squared plus y squared is constant. The same idea here, right? If I take this little rectangle, I let dx dy go towards 0, everything is constant. And then I substitute dm for total mass times 2r over r squared, pi cancels out, dr. And now I integrate over r, and r goes from
0.
to capital R. And now this is something that you can easily solve. I want to give this one last try. Maybe if you hook up your computer to this.
The problem is I don't have battery, so maybe I can just place it there and then
Or we come to you. So we get the experiment to you. And while Marcus is setting up, here's the idea. What did I bring here? I basically brought a flywheel that's attached to an axis, which I hold here, and then in the back I have a little motor. And this little motor is basically my angular momentum generator, because it can spin up this flywheel to a couple of thousand RPM. The whole thing hangs on a thread, hangs down like this. Yeah. Why is it hanging down like this? Why is it not standing up like this? Well, because if I hold it here and there's mass here, gravity pulls down and I get a torque this way. So this thing experiences a constant, if it's hanging like this. Is that a no?
I think there's a vacuum control. Now it's on the lamp, right?
No.
No? Okay. It was on for a few seconds, but then it switched off again.
Should I turn this on again?
Could, but I doubt it's going to do anything.
Is this connected?
The problem is with the Arduino, because the on lamp should definitely be on when it's connected to the computer, but it's
Anyone bring an Arduino? No.
that's it.
But you got
This
it.
one's dry, right? No, maybe it's not. No.
Or did we fry this guy?
Maybe you tried the UC. Oh yeah, now it's on.
Where did the smoke come from? Did it come from here or from here?
Yeah, I think the ESC is broken.
Oh, that's
So
disappointing.
yeah,
Okay.
that's unlucky.
No. Okay. That tables this. Sorry about that. Let's think about this theoretically, and then I'll show you the demo next week. And I want to draw a top view of this guy. This is rotating. In which direction is the angular velocity vector pointing? This way. Right? If I start it. In which direction is the angular momentum vector pointing? This direction, right? So what I have here is a huge angular momentum generator. Okay, now I hold it, I spin it up. We will do this on Thursday if we get a motor controller going. Until then, and I let go. What will happen? Well, this whole thing gets a torque. In which direction points the torque? Right? And the idea is basically I'm looking at this from above, so gravity points down. I'm holding it here. Gravity acts somewhere there, pulling this down, so I get a torque. In this direction. And this is my torque. What does that mean for the angular momentum? Right now, different, right? What I just showed before was no torque. Angular momentum is constant. Now I get a torque. So the angular momentum will change over time. In which direction? In this, right? Change in angular momentum is equal to, here we go, right? To the torque. So my angular momentum vector is changing this way. And those two should be the same, right? That's my change in angular momentum. What does that mean, right? I get an angular acceleration this way, right? So angular acceleration this way, you're sort of pointing to it, would mean something like this. And my hope is that everyone thinks this, because this is, of course, wrong, right? We're saying I have a torque, change in angular momentum this way, so I get an angular acceleration about this axis, and that basically means this thing falls down. And this is what our intuition would tell us, right? It falls down. But we already have this huge angular velocity this way. And because we have a huge angular velocity this way, an angular acceleration means all of a sudden something completely different. It basically means I take that vector and I rotate it this way. Right? If I have an angular velocity vector pointing this way, I have an angular acceleration that way. What it basically means is I rotate my angular velocity vector over here. So this thing will not drop down, but will move in a circle. That's the demo that I may be able to show you next Thursday. And to me, that seems, on first glance, completely counterintuitive, right? I have a torque that should push you down, and the reaction is that it rotates about exactly the opposite axis. But that has to do with the fact that I have already a large angular velocity about this axis. And basically, what I'm trying to do with this is that at some time before this, I had an angular velocity in this direction. And then after some time, I will have an angular velocity about this direction, right? If I look at this, so this will move over here, I get a change in the direction of angular velocity. And if I look over this over finite horizon, I see it change from here to here. I could do this in a completely different way by having two of these and saying, well, this one was turning. Let's turn it off. So I use the motor to create a torque in the opposite direction, which would require a torque that way, right, to stop this flywheel. And once it's stopped, I would say, OK, let's turn this guy on. So I use the motor to turn the flywheel on, which would require a torque in this direction. Right? So in a sense, changing the axis of rotation is the same as canceling this rotation and starting this rotation. And if I do this with a motor, I would first stop that flywheel and then turn that flywheel on. And then if you go ahead and look at what is the effect of these two, it's an acceleration, and change or angular acceleration moment exactly about this axis. So the part that always sort of tricks our intuition is that if I look at something like this and I say, what's an angular acceleration about this axis, you think this rotation. But if I have a large velocity where my vector already points that way, I'm not changing the magnitude, right? If I run this motor, what will happen is that that vector grows and grows and grows and grows and grows. And now I have a different option of changing angular velocities by rotating the axis or changing the axis of rotation. And that is, of course, much more efficient. Right? If you think about, you will see this, right? Running this up takes about 2 minutes with a motor. And then, in a sense, changing the direction with the motor would be 2 minutes slowing it down, and then another minute, 1 minute slowing it down, and another minute spinning it up in the other direction. I could also just flip the axis, right? Which has the same effect, changes the the direction of rotation in a fraction of a time. And if you think about angular velocities and angular accelerations that way, right? If I have a large angular velocity, changing the axis has a huge effect. And this is why you start feeling these huge forces if you move the axis around. Sorry for, well, not showing this, but we'll work on it. And then I will promise I will not touch it before class on Thursday, and then you get a demo. Thanks.